hoping to get through all of this, or almost all of this today, so that we don't fall behind. It depends, because right now we're in our APR process, and so I may get called out, I don't know. And then we have to leave. So we're just continuing right on right where we left off. Now we're going to start to use chemical logic and some of these common biochemical reactions that you're going to see over and over and over and over again. It's one of the reasons why I can't stress it enough. If you keep your handy-dandy enzyme glossary, tool belt, whatever you want to call it, around, it's going to help you a lot, because they're going to help you figure out what kind of reactions occurring, what are the possibilities, what can you completely negate, all that kind of stuff. And so there are so many possible metabolic pathways. This is from Roche website, and now I think they actually have an interactive one. I mean, it was interactive before, but now I think they actually have an app or something that you can get where you can look. This is from a single cell. This is bacterial. I think it's supposed to be E. coli. But you will be able to see how they interplay with each other. One other thing to notice, you can see some certain shapes, because some of the metabolic pathways are circular, some of them are spiral, there are some that are just linear for the most part. And then there's at least one that, in my mind, it kind of looks like shoelaces or something. It's like a lattice work. It's really, it's pentose phosphate pathway. Okay. All right. And so, but you can click on this. That's actually, it's a great tool. It gives you the names of the enzymes, substrates, lots of different things like that. It's really, really interesting. But by the end of this semester, we're going to actually be able to see and go over a lot of these different types, okay? So for cellular metabolism, if we just looked at that single cell, the types of reactions there, I mean, it is overwhelming, right? There's so much that can go on. So don't sit there and memorize every single thing, okay? I want you to be able to understand the patterns and be able to use the logic behind it in order to figure out, okay, pyruvate kinase, which is one of the enzymes that you're going to be learning about soon. Pyruvate kinase, what kind of enzyme is it? If it's a kinase, what do kinases do? They transfer phosphates, add phosphates, what else? Using ATP or GTP. So if you have pyruvate kinase, it's going to require ATP, and what's it going to be adding the phosphate to? Pyruvate kinase. Pyruvate. Okay, so that's why I've been saying that it makes a lot more sense. Okay, not every organic chemistry reaction can occur within the cell. So if you're in organic chemistry now, or if you've taken organic chemistry already, you know, for example, one example I always like to use is hydrogenation reaction. You know, in organic chemistry, you learn it takes like a platinum, palladium, or rhodium, you know, electrode, and you have H2, or, I mean, obviously we don't have like that going on. So there are certain types of ways that we can get around that. You're going to see a lot of these things over and over and over again. Okay. And yeah, once you just look for these patterns. Okay. On your own, I want you to go, because this is stuff from Gen Chem or early organic chemistry, to review what homolytic versus heterolytic cleavage means. Homolytic means that the bond between the two breaks the electrons, one goes to each of the parent atom, versus heterolytic, one parent atom needs both electrons, so you get something that's negatively charged, something that's positively charged. What a nucleophile is versus an electrophile. What do all nucleophiles must have? Lone pair electrons. Okay, so electrophiles have to be something that's either positively charged or delta plus. This came right from your book. It shows the different examples that we have, and so on your own you can look at that just for time's sake. And this is actually repeated. They showed this, I think, in the very first chapter, and then it's repeated once again, the different types of nucleophiles and electrophiles in biochemistry. So on your own, you want to review all of that. Okay. Most reactions are going to fall into one of 5 general categories. They're not necessarily mutually exclusive, because sometimes we'll see an enzyme complex may have more than one. Okay? So you need to know the 5 types of reactions that you're going to see over and over and over and over again in biochemistry. 1. Okay, what is one type of reaction that you think you're going to see? Pardon? Hydrolysis. A hydrolysis reaction? Okay. So whenever we're doing hydrolysis reactions, what's actually happening?
Oxidation reduction.
Okay, there's oxidation reduction. That can be different than hydrolysis.
Yeah, that's different.
Okay, way that I remember this, by the way, so there are 5. And if you go into graduate school, medical school, you're going to learn lots of acronyms. I remember IFROG. Okay, so oxidation reduction is one of them. It's the O. So those are redox reactions. Okay. Then you mentioned hydrolysis. What kind of broad category is hydrolysis? What's happening in hydrolysis?
Breaking of bonds with water.
Yep. You are going to have reactions that make and break bonds. Typically, we're talking about carbon. In biochemistry, we're talking primarily carbon-carbon bonds.
Synthesis.
Okay, that would go with the making things.
Oh, sorry.
Okay. But yeah. What else is there? What do you suppose we have I, F, and G left?
Switching bonds around.
So what is that called?
Isomer.
Isomers. So those are isomerization reactions or internal rearrangements, either way that you want to think of it, because that's the same thing. It's just that your book may say internal rearrangement. Okay, we have F and G. What else is there? You guys are doing pretty good so far. You go out in the sunlight, what's bad? You go out, the UV light, why? What?
You said farm insulation, you know.
No, you go out in the sunlight.
Talking about free radicals?
Free radicals! So free radicalizations.
That's literally all I was thinking.
Free radicals. Okay, and then we have the G. What is the one thing that we haven't discussed yet that we actually, for example, pyruvate kinase, what does it do? Group transfers. So, you don't have to remember it as iFrog, but I don't remember. One of my very first years of teaching biochemistry, someone came up with it. It stuck with me, so. Okay. All right, so then now we're just going to go through. So this isn't actually in the order for iFrog, but that's how I remember where I'm going. So now we're just going to start looking at some of these. These are for reactions that make or break. So this is the R. And okay, good. They can use either a nucleophilic carbanion, which what is that? What's a carbanion? I didn't have you guys for organic chem 2. It's a carbon that's negatively charged, so it can be a nucleophile. And you can have an electrophilic carbocation, which would be positively charged carbon. Okay. These are chemically impossible in vivo. You will not just have a straight carbocation floating around. Okay, they have to be protected somehow. You've got to stabilize them some way. Many times, biochemists would like to call them electron sinks. I don't think it's a very weird term. But that way it helps stabilize some of these charges and things because they can pull the electrons down the electron drain. I don't know what they call it, C. Right? And so in particular we're looking at, I call them amazing, I don't know why I made it, but the carbonyl and the imine. Those are the two biggies that are electron sinks. Okay. And then I've also just included the fact that some of these specialized cofactors like TPP, which is thymine pyridoxal phosphate, can also help with that. We'll find out like magnesium a lot of times, there are phosphates around, it's used. But if we think, what's a carbonyl look like? Obviously it's got a carbon. What makes a carbonyl?
Double bonded to an oxygen.
Yep, because this is delta plus, that's delta minus. Of course, we got ch13. So we can have things just come and smack that carbon to break this bond. Okay. And then we have imine. What is an imine? Which is one that I don't know that you discuss due to time constraints usually in organic chemistry too. You can probably just mention it briefly. Whereas like a in-between step, because in synthesis, I don't know that they use it as often. Our body uses it a lot. Okay. What is an imine? It sounds a lot like.
It's a carbon double bonded to an nitrogen.
It's a carbon double bond to a nitrogen. Okay. Because it sounds a lot like an amine, but yes. Remember, nitrogen actually has another bond there as well. And we have something very similar, delta plus, delta minus, and so we'll see that over and over again. Oh, right. So this is what it's trying to show. Some of the different scenarios that we've seen to make like enolate. The one on the far right, upper right hand, that's called an enolate. Because it looks like an enol, but it's it's got the negative charge, so it becomes an enolate. We can see if it's a carbanion that's next door to the imine, you can also have it come form. Does anyone remember from organic chemistry what this is called? It's one that I just like to say because it's fun. This formation. It's an enamine. Because it's an ene and an amine, so they call it an enamine. Okay, and then usually in order for this to happen in vivo with the carbonyls, what we'll see, because a lot of times sometimes we draw it as being an oxygen anion, but many times it's going to be stabilized by either a metal like magnesium or manganese or something like that, or even sodium, lithium, or it's going to have a general acid next to it to help stabilize it. So something like aspartic acid, histidine, things like that. Okay. So here are some of the common reactions. Let me make it smaller so that way you can see. You should have covered aldol condensations in organic chemistry too. They also happen in vivo. One example that we're going to see very shortly, I think it's the very next chapter, is called aldolase. It's one that people usually forget the name. But aldolase gets its name because it uses an aldol. Which what is an aldol?
Aldehyde alcohol.
Aldehyde and alcohol. So if you look at the product there, they also call them aldol condensations even when there's a ketone in the final formation as well, by the way. But okay. So we have an aldol condensation reaction. You can have Claisen reactions, just like what you see in organic chemistry. This is an example from in vivo citrate synthase, which is part of the citric acid cycle, or Krebs cycle. If you notice, we see that one that says CoA-S. Does anyone know what that is? What is this? This is the way that they like to abbreviate it in.
Coenzyme A.
That's coenzyme A. Sometimes I even abbreviate coenzyme A as CoAsh when it's free, and then it becomes acetylated or acylated. This is when it's been acylated. Well, technically, this one is acylated. Okay. That's a Claisen ester condensation reaction. You can also have one that I always liked talking about in organic chemistry, just because I knew that it had a lot of relevance in biochemistry. I don't know that Dr. Salvatore's would point it out as often, but they're decarboxylation reactions of beta-keto acids, which are a mouthful. But we see this a lot. We will see it in the breakdown of our fats, and we'll see it in, for the respiratory processes. Okay, so why is it called a beta-keto acid? What makes a beta-keto acid a beta-keto acid? What does the beta indicate?
Second from the alpha carbon.
Not second from the alpha.
I mean, first from the alpha.
First from the alpha. So this next term is my word. Okay, so let me change color. The whatever carbon's getting priority, I called that one the ground zero carbon. So based off a Greek lettering system, the next carbon would be C alpha and 2 would be C beta. Okay, and that beta, the carbon that's beta to it, has special superpowers. It doesn't really, but based off of, they're not actually showing the reason why here, but it's easy to decarboxylate from it. Do you guys remember this from? And just like it's also has special reactivity because it's the beta carbon. Do you guys remember this from organic chemistry? We'll see this mechanism over again a few times. Remember, here, let me show it then. I'll use a different color than what they use. So they're not showing the in-between step, but you always go from things that are negatively charged or delta minus, right, towards things that are positively charged or delta plus. So we have boom, sound effects optional. Something's got a break or a give, and so what happens, and the way I usually would have drawn it to indicate the reason why that the C beta was so special, is this bond breaks, but the interim step is it actually goes over to form a double bond to the C beta, and something's got a break or a give, boom. And so that's why the in-between step would look like this. Or the C beta actually would have like an oxygen anion. Or, once again, you could have like a general acid or a metal nearby to help it out, to make that enolate. Then you get collapse. So if you had a need for organic chemistry, anytime we see stuff like this, we'd have a collapse. So boom, sound effects optional once again. Something's got a break or give, and it's that double bond, and it swings out and it attacks whatever needs to be attacked. And here they're showing this in hydrogen. It's more basic looking thing. So that's how you decarboxylate. That's one way that you can decarboxylate. All right. So the second type are those isomerizations. Technically, they can also be elimination reactions. These are all intramolecular rearrangements of some sort. Notice they do not, that's what makes them so special, is they're not going to affect the overall oxidation state. That's the biggie. The individual atoms can undergo redox chemistry, but overall, the molecule has to be unchanged. Okay. Just check to make sure that I didn't. Okay. So, look at an example. Give me a moment to sink it in. Also to think about possible names and what kind of class of enzymes and stuff like that would be. We see this a lot with adjacent carbons just swapping. It's like swapping things. Okay, so we go from glucose 6-phosphate to fructose 6-phosphate. Okay, it's a part of glycolysis. Okay, and the way it does it, for example, is you have some type of general base here that's going to abstract the carbon, it's hydrogen off of it. Boom, sound effects optional. Boom, you have a general acid. So you make this dienol. No, that's not right. An enediol. Okay. Oh, it's written right there. Should have just looked. Okay, enediol right there. And then you just get the reversal. The base gets its hydrogen back, and then it takes the hydrogen from what will be the general acid. And so you just swap to places. Okay, what class or classes of enzymes can this be? In this specific instance here, glucose 6-phosphate to fructose 6-phosphate.
Isomerase.
It's an isomerase. That is correct. Okay, notice it is reversible. So if you were going to name this one, what would be some possible names?
Glucose 6-phosphate isomerase.
It could be glucose 6-phosphate isomerase. What else could it be? reversible. Fructose 6-phosphate isomerase. It's not very picky. It goes frontwards and backwards. So many times this one's called phosphohexose isomerase. But see, if you had told me glucose 6-phosphate isomerase or fructose 6-phosphate isomerase, you'd get most, if not all, the credit for it. Because if you tell someone that, they would be able to, knowing what we know now, figure out what's going on. Yeah, but this one literally means phosphorylated 6-carbon sugar. Yeah. Moves it from place to place. Okay. Any questions so far? So here's an example of an elimination reaction that doesn't alter the total oxidation number. You'd have to sit down and figure it out and find out. Condensation reactions to form alkenes typically do this, and the reverse. Technically would fall under this kind of thing. So, and we'll actually go over fumarase and citric acid cycle. I forgot what chapter that one is. Okay. The third type are the free radicals, which are really cool. They can be bad. However, sometimes they are necessary. Free radicals are special in the sense that they are homolytic. They have to be homolytic in order to become a free radical. They are important in biochemistry for a number of reasons. Sometimes isomerizations. One example is using cobalamin. Those are the cobalamin dependent ones. This is vitamin B12. If they use SAM, SAM is also called, does anyone know what this is? It stands for S-adenosylmethionine. Given that, I would expect you to know what it looks like. Okay, I don't ever ask you to draw out the adenosyl part, but you know where does adenosyl come from? It's adenosine, which is, what is adenosine? It's a nucleotide. What nucleotide is it? A. Okay, from RNA. Okay, so it's an A. What does the S stand for, Sam? What does the S stand for?
The way that light is refracted.
Not this time. What is special about methionine?
It's got sulfur in it.
It's got sulfur. It's not thiol. But it's got sulfur. What is that functional group called? Sulfide. Okay, so what could this mean? I don't think the S is the locant. It tells you that the A is attached to the methionine through the S. But SAM's easy to remember. S-adenosylmethionine. It also, for whatever reason, well, actually another reason, it has another name, another common name that, even though I'm not a big Star Wars fan, to me it sounds like something from Star Wars. Anyone know what else is called? And I don't know. It's always made me think of Star Wars. It's called Adomet. For adenosylated methionine. So Adomet. I don't know. It sounds Star Wars. It's Star Wars-esque. Okay. There are certain types of carboxylations. There are redox reactions. One example for that would be ribonucleotide reductase. DNA photolyase, which is rearrangement. Okay. Which has to do with photoadducts in DNA. So let's move to the next group. This one, there are so many examples that let's go on and on and on and on and on and on and on. Okay, these are group transfers. To me, they're also the easiest one to explain. We've already talked about kinases, which transfer phosphate groups using ATP or GTP. What happens? What's the class of enzymes that transfer phosphates that do not use ATP or GTP or any NTP? What are they called? What are they called? You need to know these. These are in your enzyme families. Not a phosphatase. You're close. Phosphatase removes it as an inorganic phosphate. So what's the opposite of phosphatase? Phosphorylase. Phosphorylase. Make sure you know these. I have a feeling there's going to be some enzyme things coming up soon. I know that there are for all metabolic pathways. You also have acyl transferases. Sometimes if they are very specific for the acetyl group, we call it acetyl transferases. But acyl is just a generic one. Glycosyl transferases transfer what? A glycosyl group, which would be a, generically speaking, it's a what biomolecule? Sugar. Okay, aminotransferases would be amino acid. Well, not amino acids, be amino groups, literally. Because you can have carboxylases or carboxyl transferases. You can have nucleotide transferases, so on and so forth. Okay. Many times we have phosphates and sulfurs that are used in biochemistry that you probably didn't get to talk about in organic chemistry too, that are used to activate a molecule. We see this over and over and over again. It's one of the reasons why we use ATP for our energy source. Because if you phosphorylate it, you're activating it since it's a good leading group. Sulfurs are also amazing leading groups. Much better than oxygen. Both those, I mean, it's much better than oxygen. Both those are. Okay. So, for one example, we have the acyl transfer. This I would expect you should know, remember from organic chemistry too. You have an acyl group is a good electrophile. This is right. We have a nucleophile of some sort. It's either going to be neutral or negatively charged. Smack. You're going to form the tetrahedral intermediate. And whenever you form the Ti, you have to collapse the Ti, and you get whatever leaving group that was there before is one that leaves. Okay. Many times this can be reversible. So that's right. It's nothing new. So that's true with an acyl group. But what about phosphates? What's the structure and the shape of a phosphate? It starts off as tetrahedral. So therefore, we don't have a tetrahedral intermediate. What kind of intermediate would we be ultimately making? What's this shape for an acyl group originally called? Trigonal, planar, to tetrahedral. Well, if we started off as a tetrahedral, how many things are going to be in the intermediate? 5. Okay, so it's a pentavalent intermediate. Okay. There we go. So phosphates are amazing because of the fact that they have so much resonance. Okay. The phosphate is very delta plus, so it's easy for it to get attacked, and it's also really good for it to leave as well. And it's called a pentavalent, which literally means 5. Shares 5 bonds. That intermediate. That's not that it's central. I don't have an example. I thought I did. Oh, I do. Okay, I thought I did. Good. So this is the example here. So this is to show, and the example they're showing this right here is a glucose that's being phosphorylated, and this is enzymatically catalyzed. So what class of enzymes can do this reaction? What class of enzymes would be doing this right here? Kinase. No, it's a kinase. Why is it not a phosphorylase?
ATP.
It's using ATP, so it's a kinase. What kinase would be doing it?
Phosphohexokinase.
Oh, you were so close.
Hexokinase.
It's hexokinase. Yeah. Because this enzyme is very promiscuous. It likes all the 6 carbon sugars pretty much. You're gonna see it a lot. You're gonna see hexokinase. There are different isoforms, and you're gonna see it a lot this semester. Hexokinase. So ultimately, though, you're gonna have an alcohol being a nucleophile. You've got ADP, which will be the leaving group in this instance. So that's what they're trying to show down below. Okay. Are there any questions so far? So now we're left with the fifth group, which are the redox. At this point, you should know the oxidation states for carbon, alkane, alcohol, aldehyde or ketone, carboxylic acid, and then ultimately carbon dioxide. Which one of these has the most potential energy? Alkane or carbon dioxide?
Alkane.
Why?
Because it has more electrons.
It has more electrons. It's the reduced. This is the fully oxidized. It's really, for carbon, it's really easy to tell whenever it's being oxidized. You're adding the number of carbon oxygen bonds. Reducing, you're adding the number of carbon hydrogen bonds. So it's got the most potential energy. Carbon dioxide literally means that our body has utilized all of the electronic potential from that carbon. And so you use it and you lose it, okay? So therefore you know, ready to get the next batch in, okay? And so you should know this series here. Okay, so some of the enzymes that are involved in this are called dehydrogenases. There's also oxidoreductases, and then there are a couple that are named one way or the other, either for historical reasons or like with respect to cytochrome C, it's because there are two different enzymes, one they can reduce and one oxidizes. And so, but there's also oxygenase, which is not on this one, which we don't cover until later in the semester. Dehydrogenases. The next one. Yep. Let's jump the gun. So just like yin has to have a yang, light and darkness, you have oxidation must have reduction. You can't separate it out. Oxidation usually releases energy. For dehydrogenases, they are going to use something like either NAD plus with NADH, FAD, FADH2, notice there is no plus there, FMN or FMNH2, no plus, or NADP plus NADPH. And the only difference between NADP and NAD plus is the fact that this one's this one's not phosphorylated. NADP has the phosphate group on it. So that's why if you were just looking, if I had only given you this name, or given you this right here, lactate to pyruvate, lactate dehydrogenase, you shouldn't be able to say immediately, okay, it's going to have to either have NAD, NADH, or FAD, FADH2, or one of their derivatives. And this one utilizes NAD plus NADH. It's not written on there, but it does. And we get that from the name dehydrogenase. Good. I'm going to go ahead and just continue on for time's sake. This is where we start to look at, I don't remember what song I used to have there, but the iPad doesn't play it. So this is where we start to look at some of the cofactors. In particular, we're going to focus the most on ATP and thioester. Oh, I really hope that I separated out these slides. I apologize if I did not. Let's see. I did not. No. That's the bad thing. Stupid iPad. So, I had it to where I could click on, where it would bring up each thing individually. All right, so let me just do it the old-fashioned way. Except you'll just have to deal with my beautiful artistry. There we go. Okay, all right, so let me go back here. So these are, these are important energetic biomolecules. I used to put a lot of music in my things before I got the iPad. Okay. The three biggies that we're going to be focusing on, as I mentioned, are ATP and other phosphate-containing molecules. And all that what happened that got overlaid was whenever I click on it, it would show what ATP looked like. So in other phosphate-containing molecules, and that's the way that many times in biochemistry we abbreviate phosphate as a P within the circle. And that's just my abbreviation for molecules. A second one are thioesters. What in God's name is a thioester? What's an ester? Don't write this part down. What does an ester look like? It has R, C, double O, O, technically R prime. Okay, so that's an ester. So what would be a thioester? The thio means sulfur. So where can we put a sulfur? Sulfur will replace what? What? No.
It's going to replace the oxygen.
Which one?
Not the double bonded one.
The what?
Not the double bonded one.
Right. The one that would be the good leaving group. So that's a thioester. Okay. We'll talk a little bit about the reasons why that's important. An example of this for the thioester would be like coenzyme A. So that's when it's a thiol and it becomes like acetylated or something. This is an acetyl-CoA. And then the third type of molecule that we're going to look at are what are called the electron transporters. And I've actually already discussed those. Those are NAD plus with its partner. It's NADH, FAD, FADH2. And they're analogs. So FMN, FMNH2, it's just like FAD, except it's missing the adenyl group. Or NADP plus, which just means it's got a phosphate on it. Okay. All right. So why do we look at ATP, these other phosphate-containing molecules? What is so special about ATP? Why use ATP? What's one thing?
Phosphates.
The phosphates. And so what is so special about phosphates?
They can activate other molecules.
They're used to activate other molecules, so a lot of times they're used to couple things together. Okay, so first off, hydrolysis of ATP, and many times these other phospho-containing groups are going to have large negative free energy changes, so therefore they can give off a lot of energy. Because of that, you can actually couple it a lot of times to an energetically unfavorable reaction to make something overall favorable. So in biochemistry, a lot of times I'll show this as a single reaction, but it's typically more complicated than that. So for example, the hexokinase, you're going to first phosphorylate something, the intermediate. Actually, no, that's probably not the best example. Like a carboxyl kinase or something like that would be a better example. You have to first phosphorylate something to the intermediate. And then one other thing, that second point is the fact that ATP actually can be cleaved at multiple locations. So let me show you what I mean. So this is showing ATP being cleaved at the terminal phosphate. But we could also see where the nucleophile could also attack here. And if so, AMP would be the product. And at least in theory, you could also attack there and then just release the adenyl group, or even, I guess in theory, attack carbon, which doesn't happen that I know of off the top of my head, and release, free alcohol. So But this is just to show you ADP and how you get out a lot of energy from it. Okay. In vivo, magnesium will be associated with ATP. So that's just to show you what it looks like. It's one of the reasons why almost always you know that if there's phosphorylation occurring at any point in time, you're going to have magnesium around with it. And there are even more compounds that give off even more energy than ATP. So this is what that's trying to show you. One example is phosphoenolpyruvate, which is commonly called PEP, PEP. And it's one of the highest energy containing compounds. So when you think, well, why aren't we, and what you think about, why aren't we just PEP based? Why ATP? And phosphocreatine, BPG is what the 1,3-bis phosphoglycerate is often called. You can see ATP with the various ways that it can be cut, hydrolyzed. This is, the PPI is inorganic pyrophosphate becoming inorganic phosphate, and it also gives off energy. You can see that. Okay. And then this one down here is actually a thioester, the last one. All right. So why are other phosphorylated compounds even better energy sources? Do you know? So if we take a look at this one, this is PEP. PEP goes on to form pyruvate when it's hydrolyzed, I should say, pyruvate, and it gives off a lot of energy. A lot. Normally, I would have you draw out what it looks like. Well, I mean, you can. If you draw a PEP and you remove this phosphate, and maybe you already know this, or maybe you don't, I don't know. What is left behind when the phosphate leaves, typically? You don't just leave the carbon by itself, it'd be a carbocation. But if you're doing hydrolysis, with water, so we have water coming in, smacking something, so, when you need it to leave, what functional group is going to be left behind? An alcohol, okay? So it forms pyruvate. The pyruvate actually, if you go back to organic chemistry, it's got two forms. The one that you see on the far right is probably the one that you're used to seeing. It's called the keto form. But it also is an enol. So remember, that's called tautomerization. When you have tautomerization, it's possible, because of that, it gives off a lot of energy. So anytime you see that type of tautomerization, there's a possibility of giving off a lot of energy. And then just in the last, actually, I'll save it for the, and this is actually where I'm going to go ahead and leave off because I want to spend just a little bit more time talking about phosphocreatine. Okay, so I'll